Welcome all. This is another lecture on differential calculus. In today's lecture, we will discuss Leibniz theorem and examples based on this particular theorem. So what is Leibniz theorem? Basically, Leibniz theorem is applicable for the higher order derivative of the product of two functions. If there are two variables u and v are in the product and we have to find the nth order derivative, then and if nth derivative of u and nth derivative of v exist, then the nth derivative of product of two variables by the Leibniz theorem is as follows. That is, the nth derivative of u into v can be defined as nc0 nth derivative of u into v plus nc1 n minus 1th derivative of u into first derivative of v plus nc2 n minus 2th derivative of u into second derivative of v plus up to ncn u into nth derivative of v. So see, we can say this is a homogeneous differential equation because each term contains the same degree. Here, degree of differentiation of first function decreases and the degree of differentiation of second function increases. Now, the main question arises whether we have to let first function as u or as v. Means हम किस function को first let करें और किसको second. So for this, a function which vanishes easily and quickly can be let as second, or in other words, a function which is not vanishable, that particular function can be let as first function, right? Or we can write it in other word, nc0 termed as combination. So the value of this is n factorial upon 0 factorial into n minus 0 factorial. So it will be 1. So we can write it as 1 into nth derivative of u into v plus nc1 will be n factorial upon 1 factorial into n minus 1 factorial. So on simplification it will be n, and the derivative n minus 1th derivative of u into derivative of v. Similarly, the value of nc2 is n into n minus 1 upon 2, and remaining part remains as it is. And similarly, for the last, the value of ncn is also 1, because n factorial upon n factorial into n minus n factorial, so n factorial upon n factorial into 0 factorial. So on simplification it will be 1. So u into nth derivative of v. So we can write it in this particular manner also. So we are moving on to the examples. So example 1, if y equals to sine m sine inverse x, then prove that 1 minus x square yn plus 2 minus 2n plus 1 into x yn plus 1 plus m square minus n square yn equals to 0. This is the first part of the proof, and hence we have to find yn0. Yn0 means we have to find the value of yn at x equals to 0. So to solve it, we first take y equals to sine m sine inverse x. So first we have to convert this entire function in the position where we can apply the Leibniz theorem. According to Leibniz theorem, firstly, we should have product of two functions. Now it is only one function. Another thing, for the Leibniz theorem, inverse trigonometric function should be avoided. So to avoid this, we first differentiate it one time directly. So let it is equation number 1. So when we differentiate it, this y is converted into y1. The differentiation of sine is cos m sine inverse x into differentiation of m sine inverse x. So m is the constant and the differentiation of sine inverse x is 1 upon root 1 minus x square. So can we shift this into the left hand side? And can we convert this function in the sin m sine inverse x? Because after differentiating, the problem remains as it is. Inverse trigonometric function is already there. So first we let it equation number 2. So we can simplify it in a manner shifting this square root 1 minus x square into left hand side. So it is y1 square root of 1 minus x square is equals to m, and this cos m sin inverse x can be replaced as square root of 1 minus sin m sin inverse x square, because we know that cos square theta plus sin square theta is 1. So the cos theta is equals to square root of 1 minus sin square theta. But this sin m sin inverse x is the y, so we can replace it. So after replacing, we get y1 square root of 1 minus x square is equals to m square root of 1 minus y square. Now the second condition exists here. For application of Leibniz theorem, power of each function should be in the positive integer, but the power here is the in the square root. So how to convert this? How to remove this square root? We can take square on both sides. So on taking square, we get 1 minus x square y1 square is equals to m square into 1 minus y square. Now the third condition exists. The power of y or y1 or y2 should be unit, but this power is not unit. So how to make it? We can again differentiate it, because we can understand it as a layman that we have to find yn plus 2, and Leibniz theorem is for yn. So there is extra 2. So we have to differentiate the function 2 times directly. But this is just for the layman. This is not the fixed method. Okay. So again we are differentiating it with respect to x. So 1 minus x square as it is. Differentiation of y1 square is 2y1 and y1 is y2 plus y1 square as it is. Differentiation of 1 minus x square is minus 2x equals to m square. Differentiation of 1 is 0. It is minus 2y and into y1. Now see, there is 2y1 in each term. So can we eliminate it? Yes, we can eliminate 2y1 from each of the term and take this right hand side into the left hand side. So it will be 1 minus x square y2 plus minus minus x y1, and take it into the left hand side. Minus is already there, so it will convert into plus m square y is equals to 0. Let it is equation number 3. Now it fulfills all the condition of Leibniz theorem. So we can apply Leibniz theorem in this particular function. So applying Leibniz theorem for differentiation up to the n time. So nth derivative of this function 1 minus x square y2 minus nth derivative of x y1 plus m square is the constant, so we can take it outside. So nth derivative of y equals to 0. Now there are the product of two functions 1 minus x square and y2. So which function we have to let as second? So y2 is not vanishable. So if we see this is not vanishable, so we can take it first. Or 1 minus x square can vanish when we differentiate it 2 times. So it vanishes quickly, so we can let it second and y2 as first. Similarly, in the second function, we can let this x2 as second, x as second and y1 as first. And there is only the y. So the power of this power will come into the suffix of y, because nth derivative of y can be represented as d ny over dx raised to power n, or in the suffix of y, that is yn, because first derivative is represented by y1, second derivative can be represented by y2, third is y3, fourth is y4. So another derivative can be represented as yn. So applying, so now see, this is the first function. So nc0, nth derivative of first function, that is the y2, into the second function, that is 1 minus x square, plus nc1, n minus 1th derivative of y2 plus a derivative of 1 minus x square. Now see, when we differentiate this 1 minus x square one time, then the differentiation is minus 2x. So x is remaining. So we have to move further. So plus nc2 n minus 2th derivative of y2 into d square of 1 minus x square, that is the second derivative of 1 minus x square. First derivative comes already from here, which is minus 2x. So again, when we differentiate, it will convert into minus 2, and then if we move further, then again we have to differentiate this minus 2, then it will be 0. So all succeeding derivative of 1 minus x square will be 0, and according to this the entire function will be 0. That's why we write here all other terms are 0. So this is the complete part of first 1 minus x square y2. Now for the second part, minus, it is outside, so succeeding as it is nc0, nth derivative of y1 into x plus nc1 n minus 1th derivative of y1 into first derivative of x. So the first derivative of x is 1, so the next derivative will be 0. So all the other terms will be 0, and plus m square yn equals to 0. Now we can open all the brackets regarding this nc0 d square. So nc0 is 1. This nth derivative of y2 will be yn plus 2, because it adds in the suffix of y 1 minus x square as it is, plus nc1 is the n, so write here n. First derivative of 1 minus x square is minus 2x, and n minus 1th derivative of y2 is yn plus 1, plus nc2 will be n into n minus 1 upon 2 into n minus 2th derivative of y2, so it will be yn, and the second derivative of 1 minus x square is minus 2. Rest terms will be 0, so it already represents, so we neglect them, and this 2 is cancelled out by this minus 2. minus nc1 nc0 is 1, x is as it is, and nth derivative of y1 is yn plus 1 plus nc1 is again n yn into first derivative of x is 1. Rest will be neglected because all the terms are 0 plus m square yn equals to 0. Now we can combine the coefficients of yn plus 2, yn plus 1 and yn. So coefficient of yn plus 2 is only 1 minus x square right here. From here it will be minus plus into minus. So n into 2x yn plus 1 plus minus minus n into n minus 1 yn minus x yn plus 1 plus n yn as it is, and plus m square yn equals to 0. Now combining, now see, this yn plus 2 is only the first place, only the one place. So this 1 minus x square yn plus 2 remains as it is. Now see, yn plus 1 is there and there. Both are negative because it is negative, it is negative. So we can take this negative outside, and this yn plus 1 can also be outside. So from here n into 2x remains, and from here x remains. So these are the in the one bracket n into 2x plus x. Same as for the yn, one function is there, one function is there, and one is there. These two are negative and this is positive. So if we take positive outside, then this m square will be at here. Now this minus n into n minus 1 written here, and this minus plus minus n is written here. Now we can take this x and this x as a common, and from here when we multiply this minus n inside, so it will be minus n square and plus n. So this function will be cancelled out. So 1 minus x square yn plus 2 as it is. From here 2n plus 1 inside and x can be taken outside. So x into yn plus 1 plus m square minus n square yn equals to 0. This is the required proof which we have to do. So now there is the second part, and the second part is we have to find the yn 0. Let this is equals to 4. So for the yn 0 means we have to find the nth derivative of y at x equals to 0. So first we put x equals to 0 in equation 1, 2, 3 and 4. So when we put y equals to 0 in equation 1 means the given problem, y equals to sine m sine inverse x. So at x equals to 0, sine inverse 0 will be 0. So the sine 0 is also 0. So the first function arises, the value of y0 is 0. Now when we put x equals to 0 in the first derivative, then it will be y10 equals to m, because y1 is equals to m upon root 1 minus x square cos m sine inverse x. So cos 0 and cos 0 is 1 and 1 minus x square is 1. So the only m exists. So y10 is equals to m. And in the third equation when we put, then we get y20 is equals to minus m square y0. But the y0 is 0. So y20 will be 0. Now putting in the equation number 4. So when we put in equation number 4, this is 0. Only yn plus 2 0 exists. When we put x equals to 0, then this entire function will be 0. And here minus plus m square minus n square yn 0. So take it into the left hand side. So it will be into right hand side. So this will be minus m square minus n square yn 0. So this is the relation from where we can get all succeeding values of y3, y4 and so on. This equation can be known as recurrence relation, and letting it equation number 5. Now we have to find the value of y3, y4, y5, y6 and so on, so that we can make a symmetry. So for this we put n equals to 1, 2, 3 and so on in this particular equation. So when we put n equals to 1, then it will be y30, which is equals to minus m square minus 1 square y10, but the y10 is m. So we can replace this y30 as minus 1 minus m into m square minus n1 square. So for the symmetry we can write this minus as minus 1 power 1. Now put n equals to 2. So y4 0 is equals to minus m square minus 2 square y20, but the y20 is 0. So the y40 is also 0. And when we have to find y60, then it will depend on y4, then it is also equals to 0, same as y8, same as y10. So the all succeeding even terms will be 0. Now we have to find the y5. So for the y5 we have to put n equals to 3. So putting n equals to 3, so y50 is equals to minus m square minus 3 square y30. But the value of y30 is minus m square minus 1 square, and 1 minus is already there, so it will be positive. Or for the symmetry we can write it as minus 1 square into m square minus 1 square into m square minus 3 square. So now tell me, if we have to find y70, then what it will be? It will be minus 1 cube m into m square minus 1 square into m square minus 3 square into m square minus 5 square. So the symmetry will goes on. So we can say yn0 is equals to minus 1 power n minus 1 by 2 into m square minus 1 square, m square minus 3 square up to m square minus n minus 2 square when n is equal to 4, and 0 when n is equal to even, because this is from n equals to 1, but this is already y2, up to the y2 we already find it. So this particular function is applicable for n equals to 3 basically. That's why we write here n minus 2, and for the symmetry we write it n minus 1 by 2 here. So this is the value of yn0. Hope you understand it. Now moving on to the next example. So the example 2 is, if y equals to x plus square root of 1 plus x square whole power n, then prove that 1 plus x square yn plus 2 plus 2n plus 1 into x yn plus 1 plus n square minus m square yn equals to 0, and hence find yn0. So to solve it, we have y equals to this function x plus root 1 plus x square power m. So according to Leibniz, this is not in the appropriate form because it contains the square root sign. So first we let it equation number 1. So first we have to differentiate it. So when we differentiate it, then m x plus root 1 plus x square power m minus 1 into differentiation of this internal function. So the differentiation of x is 1 plus differentiation of 1 plus x square power half is 1 upon root 1 plus x square, 1 upon 2 into root 1 plus x square, and the differentiation of 1 plus x square is 2x. So that 2 is cancelled out by the denominator 2. So it is 1 plus x upon root 1 plus x square. Now we can take common from here or LCM from here. So it will be square root of 1 plus x square plus x. So this will convert into x plus square root of 1 plus x square power m minus 1, and 1 is from here. So it will be power m, and take this into the left hand side. So y1 square root of 1 plus x square is equals to m x plus root 1 plus x square power m, but this is the y, so we can write it as y1 square root of 1 plus x square is equals to my. Now still this square root sign remains. So how to eliminate it? We first let it equation number 2. So to eliminate this square root sign, we squaring both sides. So it will be 1 plus x square y1 square is equals to m square y square. Now one problem eliminated, but the another one arises. Now the y and y1 contains power 2. So to eliminate this power 2, we can again differentiate. So when we differentiate it, first function as it is 1 plus x square. Differentiation of second function y1 square is 2y1 into y2 plus y1 square as it is. Differentiation of 1 plus x square is 2x equals to m square. Differentiation of y square is 2y into y1. Now each term contains 2y1. So we can eliminate this 2y1, and taking this into the left hand side, we get 1 plus x square y2 plus x y1 minus m square y equals to 0. Now this is in the appropriate form. So let it is equation number 3. Now we can apply Leibniz theorem here. So how to apply? Nth derivative of 1 plus x square into y2 plus nth derivative of x y1. This m square is the constant, so the nth derivative of y. Now the again question arises whether we take it first or this first. So this 1 plus x square will vanish easily, so we can take it second, and this y2 as first. Same as here, this x will be second and this will be first, and this is the only function, so this n will comes into the suffix of y. So nc0, nth derivative of first function, that is the y2, into the second function, plus nc1, n minus 1th derivative of y2 plus first derivative of 1 plus x square. So it will be 2x. So again we can differentiate it. So plus nc2, n minus 2th derivative of y2 plus second derivative of 1 plus x square. So the second derivative of 1 plus x square is 2. So this is the constant. So again if we differentiate it, then the differentiation of 2 is 0. So the all succeeding terms will be 0. That's why we write here. Plus now for this particular function, nc0, nth derivative of y1 into x plus nc1, n minus 1th derivative of y1 into differentiation of x, and the derivative of x is 1. So all the coming terms will be 0, and minus m square yn equals to 0. Now we can simplify these all two brackets. So NC0 is 1. Nth derivative of y2 is yn plus 2 into 1 plus x square as it is, plus NC1 is n minus 1th derivative of y2 is yn plus 1, and the first derivative of 1 plus x square is 2x, plus NC2 is n into n minus 1 by 2, and n minus 2th derivative of y2 is yn, and the second derivative of 1 plus x square is 2. Now from this 2 we can cancel out this 2, and plus first NC0 is 1, nth derivative of y1 is yn plus 1 into x, plus NC1 is n, yn into first derivative is 1, minus m square yn is equals to 0. Now we can write this entire function in this particular manner: 1 plus x square yn plus 2 plus n into 2x yn plus 1 plus n into n minus 1 y, and plus x yn plus 1 plus n y, and minus m square yn equals to 0. Now combining the coefficients of yn plus 2, yn plus 1 and y. So the yn plus 2 is only this particular function. So we can write it as 1 plus x square yn plus 2 plus yn plus 1 is there and there. So we can take it outside. So n into 2x plus x and minus yn. So m square minus n into n minus 1 yn equals to 0. This will be equals to 0. So from here this x can be taken outside, and this from this minus n this function will cancel out. So this function arises which we have to prove, letting it as equation number 4. Now we have to find yn0. So to find yn at x equals to 0, we can put y equals to 0 in equation 1, 2, 3 and 4. So when we put y equals to 0 in equation 1, then it will be 1. When we put in equation number 2, then y10 is equals to m. When we put in equation number 3, then y20 is equals to m square y0, but the y0 is 1. So y20 is equals to m square. So now putting x equals to 0 in equation number 4, we get this yn plus 2 0, this function will be 0, and it is n square minus m square yn 0. And when we take it into the right hand side, then it will be minus n square minus m square, or taking minus inside, so it will be m square minus n square yn 0. Let it is equation number 5, and this is known as recurrence relation. So we have to make a symmetry. So for the symmetry, we have to find y3, y4, y5, y6, 0 and so on. So for this, we put n equals to 1, 2, 3 and so on in equation number 5. So when we put n equals to 1, then y30 is equals to m square minus 1 square into y10. But the y10 is m. So y30 will be m into m square minus 1 square. Now putting n equals to 2, y40 is equals to m square minus 2 square y20. But the value of y20 is m square. So y40 will be m square into m square minus 2 square. So when we put n equals to 3, then y50 is equals to m square minus 3 square y30. But the value of y30 is m into m square minus 1 square. So y50 will be m into m square minus 1 square into m square minus 3 square. Now similarly for the y60 it is equals to m square minus 4 square y40, but the y40 is m square into m square minus 2 square. So y60 will convert into m square into m square minus 2 square into m square minus 4 square. Similarly, we can get y70 which is equals to m square minus 5 square into y50, but the y50 is this function. So y70 will be m into m square minus 1 square into m square minus 3 square into m square minus 5 square. So we can succeed it in this particular manner. We can get the value of y80, y90, y10 and so on. So there are two kind of symmetries. One is for odd terms and another one is for even terms. For the odd term, we have m into m square minus odd term square, and for the even terms, we have m square into m square minus even term square. So we can write it as yn0 is equals to m into m square minus 1 square into m square minus 3 square up to m square minus n minus 2 square when n is odd, and m square into m square minus 2 square, m square minus 4 square up to m square minus n minus 2 square when n is even. So this is the required yn0 for the given problem. Hope you understand this entire lecture of the Leibniz theorem and its supporting yn0. We will meet in the next lecture with a new phenomena. Hopefully, we will discuss partial derivative in the next lecture. So stay tuned. Thank you.